Welcome all to the start of lecture 4. This lecture is going to start a series of weeks for the remainder of the semester where we're going to be looking at things that are quite a bit less quantitative than we had in the first half of the course. So we're going to start today by looking at group theory operations. Now, group theory is actually quite a very complex study of mathematics. It's a very systematic treatment of symmetry. We are just going to be focusing on the symmetry of molecules and orbitals, and specifically how it works with point groups as opposed to line groups or plane groups. So we are actually just going to be touching a very small aspect of group theory, but it is a very powerful method that we can adapt to chemistry, molecules, and orbitals. Now, the core of group theory is something that we call the symmetry operation. And there are several symmetry operations that we're going to explore today. A symmetry operation can be something like a rotation of a molecule along an axis, a reflection through a plane, or an inversion through a point, just to name a few. Now, each symmetry operation has a symmetry element about which the symmetry operation takes place. So again, it can be a point, it can be a line, or a plane, and we'll see all of those aspects in action today. So again, we're going to focus on point group symmetry, but we will still have symmetry elements of points, lines, or planes. So here's just a summary of some of the symmetry operations and elements that we have. We have something that's called an identity, which every single molecule has an identity operation. It's denoted by the symbol E. That's essentially, does it act as itself? And so every single molecule has an identity operation. It's kind of like saying, it's a little bit like multiplying by 1. We have things that are called an n-fold rotation axis, and those are denoted as Cn. And what that is a symmetrical rotation of a molecule around an axis, and the number of degrees is 360 degrees divided by n. So if you take a molecule and divide it or rotate it around a number of degrees around an axis of 360 degrees divided by some value n, and you get the exact same molecule, looking the same way, then you have a symmetrical rotation. We have mirror planes, which are given the symbol sigma, and oftentimes your mirror planes can be labeled with subscripts as sigma v, meaning a vertical plane, sigma h, meaning a horizontal plane, or sigma d, which means a diagonal plane. And what this is a symmetric reflection across the plane, kind of like your hands. If you hold your hands up together, you see that they reflect each other. So if you held your right hand up to a mirror, the reflection would look just like your left hand. Then we also have a center of inversion, which is given a letter I, and this is a symmetric projection of a point through a point of inversion. And if you take all of the points of a molecule and move them through the point of inversion, you will get to a similar point on the other side of the molecule, essentially. And then we have an improper rotation. So an improper rotation is given the letter Sn. Again, that n is indicated by degrees, 360 degrees divided by n. And the improper rotation is a composite operation. So it's always a rotation of 360 degrees divided by n, followed by a reflection that is perpendicular to that axis of rotation. So let's take a look at all of these in a little bit more detail. So here, if we have rotational symmetry, we can see that we've got something like an ammonia molecule here, NH3, with N in the center, and then our 3 hydrogens. This has a C3 rotational symmetry. We have the hydrogen here that we just star so we can keep track of it. And if we do a C3 operation, now where does that 3 come from? In the case if you take 360 degrees and divide by 3, you get 120 degrees. So if I rotate my ammonia molecule 120 degrees, I have this hydrogen going right here, as we see here. This hydrogen rotated 120 and went here. And this hydrogen rotated 120 and went back up to the top. Okay, so as we can see, these two pictures here are completely identical. other than we're just tracking one of the hydrogens. But that indicates that this has a rotational symmetry of 120 degrees. And to get 120 degrees, take 360 divided by 3, and you get 120. Now, I also have a little bit bigger symmetry element here, and this is a little bit more complex, but sometimes you'll see a rotational symmetry with two values on it. You would see something like a C3. 3 is a subscript that tells us what the n value is, and then it might have a little 2 or some other number up here. And what this tells me is that I can do a twofold rotation of 120 degrees. So basically a 240 rotation, a 240 degree rotation, and still get back to my original molecule in appearance. So if I take my original molecule here, see my start up at the top, and I do two C3 operations, I get down to here. And I could do another one, and that would take it down to here, and then another one, and that would take it up to here. So it's still a C3, but it's a doubled C3. And that's all that means, is that it gives me an additional rotational symmetry around the same axis. It is considered to be a separate symmetry operation. We talked about mirror planes, and so here are some of our different mirror planes here. So this might be like a square planar molecule, or it could be a tetrahedral molecule looking down from it. We can't really tell from this aspect. Square planar is the easiest one to envision. So we have a C4 rotational axis here, so that tells me that this is square planar and not tetrahedral. So envision in your mind a square planar molecule. So we have C4 because we can rotate 90 degrees, 90 degrees, 90 degrees, 90 degrees. Okay, and we have several different mirror planes here. We have a sigma V mirror plane, which is right here. So this is a mirror plane that's sticking out of the plane of your screen and going through these two molecules. It is parallel to this rotation axis, and because it's parallel to it and running through it, we say that it is a sigma V. We have the blue square around here. That is a horizontal mirror plane, so it is perpendicular to our primary rotation axis, and the primary rotation axis would have the highest value here, so this is a C4. And so that's our sigma H, horizontal mirror plane. And then we have a sigma D here. So your sigma D here is also parallel to the rotation axis, but it bisects two other axes of rotation. And so it bisects the sigma H, and it bisects the C4 and the C2. We also have some C2s, rotation axes, where we can flip this molecule around 180 degrees, and it just takes this atom, puts it here, and these two atoms don't move. I also have another one here that allows me to flip it around this axis, and this molecule would move here. This atom would move here, this atom would move here. There's another C2 axis right here, as we want to flip it that way. So lots of different aspects, lots of different symmetry elements just in this little molecule here. If you want to look at the difference here, not difference, but sometimes you can have two different sigma V planes. So you can have two mirror planes that are parallel to the primary axis of rotation. So if we look at a water molecule here, it's going to have a C2 axis because I can rotate my molecule around that axis through the oxygen atom, and the two hydrogens just reflect upon each other or go around. And so I can have a mirror plane that goes through the molecule here, and that reflects this atom here and reflects this atom over to here, as we see in the image to the right. I can also have a mirror plane that just cuts the entire molecule in half, all of the bonds and all of the atoms in half, and that just reflects this half of this atom onto the other half, this half of this atom onto the other half, and this half of this atom onto its other half. So we have two mirror planes there. So we denote that just with a prime. So we have sigma V and a sigma V prime. The inversion center is one that's a little bit harder to see. So your inversion center is always going to be in the immediate center of the entire molecule, hence the term inversion center. Not every molecule has one. They are actually fairly rare, but you do run into cases where they have them. And we can see the inversion center here, atom 1, and move it through that inversion center the exact same distance away as it was prior. I would put it on atom 6, and I can invert atom 6 and put it on atom 1. I can take atom 2, and that inverts to atom 4, and atom 4 inverts to atom 2, and I can take atom 3, that inverts to atom 5, and atom 5 would invert to atom 3. And so that's exactly what we have in this bottom picture here. So it's just where those atoms end up when they get inverted. And the last one here, the composite operation, is called an improper rotation. These are probably the hardest to see visually when you're having a molecule, and it really helps if you have a physical model. So remember, an improper rotation is a rotation around an axis followed by a reflection across a mirrored plane that is perpendicular to that rotation axis. So here we have a molecule that looks like it's in somewhat of a tetrahedral arrangement. So if I do a C4 operation, so this would be an S4, that's not a very good S, S4 symmetry operation, improper rotation. And the 4 comes from the fact that I can do a 4 rotation, a C4 rotation. So if I do a C4 rotation, because it's C4, it means I'm going that 360 degrees divided by 4, so I'm going 90 degrees through that axis. And so this atom just moves up, this atom moves down, this one moves to the back, this one moves to the front, just like we have right here. And now we're going to put a mirror plane that is directly across or perpendicular to that axis. I'll put in the axis here. So the axis went through the molecule like that, and you can see that mirror plane is exactly perpendicular to that rotation axis. And now when we reflect that, the yellow one is going to come over here, the purple one is going to come over here, the green one is going to come over here, and this guy is going to go over up in here. And so what we end up with is this molecule down here on the bottom, and even though the different atoms are in different places, if they are the same atom, so if these were all hydrogen atoms or all chlorine atoms or whatever, the molecule would still look exactly the same. It would have the exact same configuration. So just a quick introduction to the different symmetry operations. We'll be talking about these as we move along, how we use them. It does take a little practice to get used to using them, so I certainly encourage you to find some problems. You can do it online. You can use AI to have it create some problems for you. We'll look at how we assign various point groups to molecules using these symmetry operations, and so we will get in some practice.